Good morning. So this is our second lecture of alkenes properties. We were discussing yesterday electrophilic addition reactions. On alkenes, we did radical addition reactions that were anti-Markovnikov. On alkenes, that is Kharash effect, peroxide effect. Today, we are dealing with four important reactions. Our main target is four important reactions of alkenes, that is HBO, OMDM, ozonolysis, and if time permits, we would definitely go for Beer's reagent, hydroxylation reactions. So these are our four important reactions of the day. Let's start. We may extend a little more than the usual today because, as you can understand, these are important points and time may be a little shorter. So today, let me first tell you in brief what we have already done. Okay, so what we have done is alkenes have pi bonds, and due to this particular thing that alkenes have this type of pi bond, they have a loosely held pi electron clouds. So they can be attacked. We studied that there are three types of main reactions given by alkenes, that is electrophilic addition reaction, free radical addition reactions, and radical substitution reactions. Yesterday we did this, we were doing this, like some of them are done, some are left. I'll just review, and this is still on hold. So from here, if I could mark, we have done hydrogenation in last week lectures. We have done addition of HX, dilute H2SO4, constant H2SO4, halogens in CCl4, ICl in CCl4, halogen in water, HBr in H2O2. This much we have already done. Okay. This much part we have already done. Now we have to start with HBO, OMDM, and ozonolysis. So in the sequence, as we have studied dilute H2SO4 reaction. So I'll first complete addition of water, that is HBO and OMDM. Okay, so first we are going for HBO reaction, which is hydroboration oxidation. HBO is hydroboration oxidation reaction. Now, what is hydroboration oxidation reaction? Let me first write net reaction for you, and then we'll go for the mechanism and other stuff. So let us have unsymmetrical alkene like this. It is a two-step reaction. In step 1, we have B2H6, which is dissolved in THF. What is the purpose of THF? I'll tell you. And on second step, we need NaOH plus H2O2. The product we get as a major is RCH2CH2OH. Okay, so what is the net change in one line if I'm asked to define what is HBO reaction? So I'll say it is anti-Markovnikov. As you can see, yesterday OH was coming to more substituted carbon. Today OH is attached to the carbon which is least substituted. So it is anti-Markovnikov addition of water without rearrangement. There will be no rearrangement of carbon skeleton, as we saw yesterday. In dilute H2SO4, there were carbocationic rearrangements, so they keep on changing the carbon skeleton if required. But here it is no such thing. There will be no rearrangement, and a direct as such skeleton will continue to the product. Okay, so how the reaction proceeds? First, let me tell you what is the purpose of this THF. As you all know, B2H6 exists as a dimer. BH3 exists as a dimer, B2H6. Now, when it is B2H6, it cannot act as a reagent, it cannot act as my required Lewis acid to attack alkenes. So, B2H6, when dissolved in THF, tetrahydrofuran, what practically happens is this tetrahydrofuran oxygen, okay, it gives a sort of coordinate to BH3. As a result, this B2H6 exists as a monomer. It makes our B2H6 in monomer. That is why we prefer THF. So you can ask then why I can use any other ether if I want. Well, theoretically you can use any ether you want, but practically it should sustain the temperature requirements because we will heat B2H6 in THF to form this monomer. So it should sustain the temperature requirement. If it could sustain, you can use any XYZ ether. Okay, so once you have got this B2H6, please look carefully. This alkene, now this B2H6, now in the form of BH3, will have a transition state like this. And to be honest, it has two more hydrogens. So it will repeat the thing from two other alkenes also. Let me draw first this transition state R, CH, this bond, one already there, one is in the process of breaking. CH2, it will form a bond with boron. Here it will form bond with hydrogen, and this is in breakage. So this bond is breaking. These two are in the state of formation. This is again breaking. 2 sigma with these H are continued. Okay. If I repeat the same thing with two more times with two alkenes, as you can see, it is sterically so very crowded. And this is the reason why always as a rule, I'll draw the complete transition state CH2, H, CH2. Now these CH2 are attached to CHR. Okay, and this CH bond will be definitely in the state of breaking. CHR, CHR. You can see how crowded the boron is, right? And if it is so crowded, boron will always attach itself to the least substituted carbon. Okay, let me complete the bond formation and breakage thing also. Formation, breakage, formation. As you can see, in a cyclic transition states, there are always alternate settings of bond breakage, formation, breakage, formation. Break, form, break, form. Now, I cannot write this crowded TSA every time. So, we are adjusting ourselves to this different form of writing. And please let me tell you that we'll have this boron attached hydrogen which is going now to alkenes with a red color, just to have till end that which hydrogen came from which or reagent we want to do this. So I can now write RCH CH2. I have intentionally not written here H, just wait, and boron. Okay, and here this is the H. Okay, this H has come from B2H6. And here itself you can see that there is a cycle formation like this. Okay, with respect to double bond, you can see the boron and H both have to come from the same side. So it is a syn addition reaction. B2H6 cannot form this four-membered cycle from opposite sides. It has to come from the same side. So it is a syn addition reaction. Now, once we have formed this, I'll represent this part in continuation with R dash for further discussions. And then in the end, I'll replace it with this particular RCH2CH2 again for your understanding. Okay, so let me start with R dash for further discussions. Now, what we have formed is R3B. This R3B will be named as trialkyl borane. We'll call it trialkyl borane. It is a Lewis acid. Yes, boron still has empty orbital. Okay, it is a Lewis acid. Now this R3B can have different types of reactions. Let me write all, and then I'll discuss the one which is required. If I'll treat it with NaOH plus H2O2, as you know, H2O2 is an oxidizing agent, we will have ROH, alcohol. This we call is oxidation. We can have another reaction that is treated with acids like CH3COH. This is direct protonation, and it is in fact called protonation of trialkyl borane. Okay, you can have HeNO3 plus NaOH. This is a radical reaction, and we have a dimerization of the alkyl groups. Okay, not much about the mechanism of this are known and are required. It is expected to be a radical reaction. Correct? But this is what is most important for us. Introduction of OH, that is the oxidation. So let me tell you how that happens. Okay, the part that we have discussed till formation of R3B, till here reaction is called hydroboration. As you can see, we have added hydrogen and boron to double bond. Correct? So till here the reaction is named as hydroboration. And now we are moving to second part of the reaction, which is oxidation. As you all know, oxidation is either addition of oxygen or removal of hydrogen or removal of electron, or I can say increase in oxidation state. So here increase in oxidation state or addition of oxygen is the best definition that we can use. Okay, for carbon. Let us see how it happens, how this oxidation happens. First of all, H2O2 being an acid and NaOH being a base, certainly the first reaction is going to be formation of such salts. Okay, now these salts are, you can see they can act as a Lewis base. O minus is there. So when our trialkyl borane comes here, okay, and this anion act as a Lewis base, there is a formation of R3B, R3, R3, O, and H, and a negative charge comes on boron. Is that absolutely clear? I have replaced the coordinate with charges. That is why this oxygen is not written with negative, and this boron is written with negative charge, as it has accepted a pair of electron from oxygen. Okay, now this B minus can act as an electron repulsive, as it has a formal charge minus. There is no extra pair of electron on this boron. Be very clear, it is a coordinate negative, formal charge negative. It is not a presence of extra electron. Okay, but these peroxy bonds are weak, are unstable. Okay, so they can break depending on the conditions. They can break homolytically, they can break heterolytically. Now, as the reaction is carried out in presence of polar reagents, certainly homolytically is not on the cards. So then what it is? So it is a heterolytic fission. Now see, this pair of electrons goes to this oxygen. So I will have a release of OH minus. Now, as and as this bond will become weaker and weaker, this O will acquire the electron deficiency, and I can write it as O del plus. Correct? This O del plus will be concertedly bonded to this R dash by the migration of R dash group from boron minus. And let me tell you that this migration of R dash from boron to O is always with retention of configuration of R dash. Okay, it is always with retention of configuration of R dash. Let me take a little risk of unshare and share because I want you to be very clear with what I want to say. See, if this is the, I can say boron, or you can take this as a boron, and this is our alkyl group. Here the oxygen is there. Let me take it this way. Here the oxygen, here this is the alkyl group bond. Okay, so with respect to our double bond, originally here was H, which is connected. Now we have this side we have a boron. So when at oxygen, this alkyl group shifts, it shifts concertedly like this. It just slide down. Okay, it just swiftly slide down from here to this side. There is no other type of movement. There is no change in configuration. So whatever bond was here is as such being formed on the other side. Correct? The bond is formed as such from the other side. So there is no change of configuration on this alkyl carbon, which was initially bonded to boron. With respect to double bond, boron and hydrogen were attached from the same side. Correct? So when it slided, the net is from whichever side the H was there, on the same side slided down, OH will now come. So coming back to what we were doing, let us see. I hope you can see my screen, my notebook. So as I said, now I was saying that there is a retention of configuration. This moves to this side with the same side. So I will have B O R dash, R dash and R dash. When this process repeats for two more times similar HOO minus attacks and such migration takes place, I will have ultimately BOR dash, OR dash, BOR dash. Okay, now again I want to replace my R dash to our original structure that we had. Okay, and original it was RCHH CH2. So coming back to our original alkyl, this is called trialkyl borate. See the word borate. 8. That is, it is an ester. Okay, it is an ester. And then it is an ester of. It is an ester of acid H3BO3 and alcohols. Okay, let me help you understand a little more that how this structure is justified. So you have BOH, you have BOH, C R dash. Okay, and esters are always formed by removal of H from alcohol and OH from acid, another. I hope this will make you realize that yes, it is an ester. This is how you can relate to the fact that what we have formed is an ester. Correct? So this ester is formed, this trial carborate is formed. As we were talking, we'll replace this R dash now to RCHHCH2. This is the H from B2H6. Okay, so now my alkyl group is OCH2. Okay, CHHR. This H is the red one. OCH2 CHHR. OCH2CHHR. This is our ester. Now, as I shown you that how this ester is formed, the reverse could be true in its hydrolysis. If I want to hydrolyze it, if I want to hydrolyze this ester back, I can simply do it by, see, HOH is water. So always remember the bond broken in this is the oxygen boron. It is not the oxygen carbon bond. Okay, so again H, OH, again H, OH. As you can see, B, okay, OH whole thrice plus R dash OH. This is coming from water. Okay, these OH are coming from water. So once you have hydrolyzed our ester, correct? So let me hydrolyze this ester. These are our H. Okay. Now I want to hydrolyze this ester. H3O plus or water is already there. H plus is already there as H2O2 was available. So taking the same consideration as we have just done, OH, H bond break, HOH bond break, okay, HOH bond break. Correct? So let me draw the structure of our R, CH, CH2O. Okay. This H is from B2H6 and this H came from the solvent in the second step, second stage. Correct? This came from B2H6. This came from solvent during oxidation. Oxidation. Oxygen came from H2O2. So this is our overall arrangement. Now, as I have told you, boron always attaches itself to the carbon which is least substituted, and in the end, we have seen that OH comes to the carbon where boron was attached. OH comes to the carbon where boron was attached. So overall in a reaction, what happens is OH always goes to the carbon which is least substituted, and this is why this reaction is called anti-Markovnikov addition, because overall certainly this OH and H, if I can just say them as H plus and OH, which is definitely not correct because it was not that we added H plus and OH directly, but just to relate it with water, I can say that it is H plus and OH addition and in an anti-Markovnikov way. Correct? It is addition of water on alkenes, but following the anti-Markovnikov method. Clear? Please remember that it is a syn addition reaction. It is a syn addition reaction. I have tried my best to make it very clear to you that it is a syn addition reaction. Okay. Moving ahead, as I have told you, I want that to be further emphasized and used, that as B2H6 always attach itself to the least substituted, this sometimes becomes very useful for us. Okay, this fact that B2H6 always prefer the sites where the substitutions are minimum, we will use this particular property in our favor. Now, what is that favor thing that I have just said? Let me tell you that given a choice, if B2H6 is made to react with unsubstituted ethene, it will certainly form CH3, CH2, whole 3 boron. It will form trialkyl borane, no issues. It will just directly form trialkyl borane. Okay, is that clear? But but if we add it, but if we add a substituted uh, a substituted alkene on this particular B2H6, then as and as the substitution increases, its tendency to attach like this decreases. Let me tell you an example. If I attach B2H6 always in THF, never without THF. If I attach it to something like this, okay, it is 2-methyl propene. If I attach to 2-methyl propene, okay, it will not be able to form so much of substitution. From here it will be connected, and it will be only connected 2 times. This is bis 3-methyl 2-butyl borane. Okay, this is bis 3-methyl 2-butyl borane, and this is called decimyl. A is missing. Let me add decimyl borane. Okay, decimyl borane. It is sometimes represented as Si alpha 2H. What is the purpose? What is the purpose of this? That if a molecule has, say for example, something like this, and we want only this to reduce or this to change to some reagent, some reactant, some product. If I write here Si alpha 2H and then I write NaOH plus H2O2, then as it is already sterically so crowded, it will avoid attack on steric crowded sites and will selectively attack non-crowded places. Okay, it will selectively attacks on non-crowded places. So we can use such reagents for our desired selectivity wherever we need this type of preferential attack at one bond and leave the other bond as such. Okay, then we can use this particular reagent. The other type of this is, there is also one more called 9-BBN. It is 9-bora bicyclononane. Okay, it is 9-bora bicyclononane. It is formed by a reaction of such cyclooctatine. Okay, and it is, as you can see, these are the 8 carbons, and on the 9th junction there is this boron. This is our 9 ppn. It is even more sterically crowded than our decimal borane. So you can use 9 ppn for the same purpose, that is very selective attack on non-substituted pi bonds if you have more than one in a compound to react. Okay, so I introduced you to two more, that is decimal borane and 9 ppn. What if in the above question they write that first there is use of 9 ppn. Now it can attack only one side. And second, they give CH3COOH, the protonation reaction that we just had introduction in the above. Okay, so if we take that type of reaction, let me tell you, this is protonation, and here this H will come. Okay, there will be formation of alkyl borane, and this H will come at this site like this directly. Okay, so if the reaction is hydroboration followed by protonation, then you have to reduce them to alkanes. If they give hydroboration followed by oxidation, then you have to convert them to alcohols. And if the reaction is hydroboration followed by HNO3 and NaOH, then you have to form a dimer. That is how these reactions proceed. Important point, anti-Markovnikov of addition of water, and overall it is a syn addition reaction. These two you have to keep in mind very, very clearly. Okay, let us move now to next reaction called OMDM. OMDM is oxymercuration demercuration, as the name suggests. Is it again a two-step process? Yes, it is. First step is oxymercuration. Second is removal of that mercury, and we'll call it demercuration. Okay, oxymercuration and demercuration. Now let me explain how this whole thing happens. What is this oxymercuration, demercuration thing? Okay, so for that to understand, let us start our reaction with first net reaction. If I have RCH double bond CH2, how will I write reagents? Now this time my first reagent is mercuric acetate, and it is dissolved in water. Can I change this solvent? Yes, you can. You can have alcohol, you can have ammonia, but that definitely will change your product. We are preferring water at this point of time because our start point was that we are preparing alcohols. It is a hydration reaction. And second, we use NaBH4 for demercuration. What we get is a Markovnikov addition of water, HOH. Okay, in short, in net, I can say it is Markovnikov's addition of water on alkenes without rearrangement. Okay, it is Markovnikov addition of water on alkenes without rearrangement. Second point is also very important. It is non-stereo specific. Unlike HPO, which was stereo specifically syn addition, I have repeated almost 10 times in last half an hour. OMDM is non-stereo specific, is non-stereo selective. Okay, it is regioselective, that I have already told you in first point, that there is Markovnikov addition, but it is non-stereo specific and non-stereo selective. Let us do how the reaction proceeds. What is the mechanism of this reaction? Now what happens is under aqueous conditions, our HgOAc whole twice is HgOAc positive plus ACO minus. HgOAc positive and AcO minus. Mercuric acetate is dissociated as a cation and an ion. That is our first step. That is how the reaction starts. What is this OAc? It is OCOCH3. This part is this. Okay, acyl. Now, my step number 2, alkenes will certainly be attacked by cations. So, this HgOAc with a positive charge will be attacked by this alkene like this. Okay. Certainly there is a formation of carbocation on this side. Okay. But mercury being a D block element, okay, being a D block element, has lot of lone pairs on its outer shells. It can immediately form a bond with this carbon. Again, an example of non-classical carbocation. This is again an example of non-classical carbocation. Okay, non-classical carbocation, as if we yesterday encountered non-classical halonium ion. Same way it is that the positive charge is not on carbon but still behaves like a carbocation. Then we call it non-classical carbocation, and this particular is known as cyclic mercurinium ion. We yesterday only studied that in this non-classical carbocation, the two bonds connected to carbon in the three-membered ring are not of equal strength. The bond which is connected to more substituted carbon will be relatively weaker. If it is relatively weaker, it is the site which will be attacked first by the reagents. Okay, it will be the site which will be attacked first by the reagents, and this is why when the solvent water now attacks, it will come on this. So I'll have RCH OH2 plus CH2 HgOAc. Correct? This will lose H plus and I will have RCHOH CH2 HgOCO-CH3. Now our main purpose in the last step is to remove this mercury. Okay, till here what we have done is we have added mercury on one side and OH on other side. So it is called oxymercuration. Okay, this is called oxymercuration. Now, what is the other possibility? I have to remove this mercury. It certainly is not that easy. Okay, removing this particular mercury might not be that easy. Well, but we have a reagent. What is our reagent? If I use NaBH4 in slight alkaline mediums, okay, if I use NaBH4 in slight alkaline mediums, it is very easy for us to remove this mercury. Last step. Okay, this last step is called demercuration. This is expected to be somewhat a radical mechanism. So here I lose my stereospecificity. H can come here, or H can come from the downside, though this CH2 is not chiral, is of no importance. But just for you to understand, there is no particular site from which I can say that it comes from this side. And what happens? CH3CO minus is released. Mercury is obtained as such. Mercury is obtained in zero oxidation state. So as the reaction completes, this mercury droplets in the container can be really appearing, can be really observed. Okay. And if we can observe such reagents, then if we can observe such reagents, then definitely there is an indication that reaction has taken place, reaction has completed. Okay, so appearance of this as droplets is seen. Appearance of this mercury as droplets is seen here. Now let us conclude what we have just seen. It is Markovnikov addition. Okay, it is Markovnikov addition of water. Point number 2, we have clearly indicated it is non-stereo specific. As the solvent is the one which is acting here along with mercury, so it is also known as solvo mercuration. Yes, sir. So, solvo mercuration it is. Okay. Then, if I use other reagents here, if I use other reagents, what I can say as other reagents is in this place. If here, in place of water, okay, when there is this non-classical carbocation formed, cyclic mercurinium formed, if I replace water over there with alcohol, if water is replaced by, let me tell two examples, by alcohol, then in the end, RCHO R dash CH3, that is ethers are formed. As now you can realize what is the word solvo mercuration. Solvent is so very important. Okay, you change the solvent, you change the product. If you use their ammonia, then here it is RCHNH2CH3 amine is formed. Okay, if you have halogens over there, you will have alkyl halide and so on. So solvo mercuration the product. Correct? And overall in HPO as well ONDM, there was no possibility of forming a rearranged carbocation. You remember one thing, whenever there is a formation of non-classical carbocation in the reaction conditions, then rearrangements are totally absent. Okay, if there is a formation of non-classical carbocation, then rearrangements are totally absent in the conditions. Is that okay? So let us move further. Next, our reaction is from oxymercuration, demercuration, we are heading to our third foremost and very important reaction called ozonolysis. This is, I would say, J favorite, even mains favorite. They have asked direct question, what are the ozonolysis products? J twisted a little here and there, but mains have asked directly from NCRT. Okay, not even mechanism required to solve a mains question based on ozonolysis. Now, what is this ozonolysis? Let me tell you what is this ozonolysis. Okay, so the ozonolysis is, as you can see from the word ozone lysis, that is the bond fission with the help of ozone. Okay, ozonolysis is the bond fission with the help of ozone. So what type of bond fission? If I write a net reaction, RCH double bond CH are different type of alkenes that I can have. Let me write those alkenes first. RCH double bond CH2. I can have RCR double bond CHR, and I can have RCR double bond C R and R. These are my different possibilities. Okay. What if I do ozonolysis, and what are the reagents? The usual reagents on these arrow you will come across is ozone followed by zinc and water. This same thing as first arrow is repeated on all the arrows. Correct? First arrow se jo hai, same thing will be repeated here also. Now, what will happen? What will take place in the reaction? Let us see that. Okay. So, these bonds will break like this. Okay. These bonds will break like this. Now, this is how double bond O will be formed. Like this. Okay. This type of double bond O will be formed. This is a very net approach we can take. So here is a formation of RCH double bond O plus RCH double bond O. Here it is formaldehyde. Here it is ketone plus aldehyde. Here it is 2 moles of ketone. Okay, we'll have 2 moles of ketone. As I am getting some messages that there is a blurred screen. Let me take help. Hello. Sir, the screen is getting blurred. Not my blurred, but on the viewer screen. I'm fine. Okay, sir. Okay, sir, I'll continue. So if there are any hiccups, they'll be correcting it, my team. So I said that this way these products, ozonolysis products, are formed. Now this is what I have written, net reaction, and I would suggest you to rely on this net reaction as far as mains is concerned. No need to go for any mechanism. This is full and final. And when this zinc is written on second arrow, it is also known as reductive ozonolysis. So whenever the word this reductive ozonolysis, don't get confused that you have to reduce the product. It is not at all required. Okay, the word reductive ozonolysis is used for the normal ozonolysis only. There is no reduction as such. Why then this word reductive is introduced? I'll tell you in the mechanism. So, for those who are interested in mechanism or for advanced, let me tell you how it proceeds. First, RCH double bond CH R dash is formed. Now, as you all know, ozone is a 1,3 dipolar ion. Okay, ozone behaves as a 1,3 dipolar ion. So here is how a cyclic addition of ozone on our alkene takes place. Okay, this is how addition of ozone, as it is a 1,3 dipolar ion, you can add it simply as one pole at one end, other at another. and there is no rearrangement, there is no change of configuration or anything. It just add in a one go. Okay, everything add in a one go, and as soon as it adds, this particular thing is formed, which is called molozonide. Now, throughout the chemistry, we keep on saying that these two oxygen-oxygen bond due to four lone pairs coming close causes repulsion and destabilize the bonds. So here, though, it is three oxygens in a row. So the structure is highly unstable. It is highly unstable and explosive. Okay, so it immediately breaks. It immediately breaks into two arrangements. Now I have to write it two ways. Let me use two different colors. Point number one is, what if this bond goes here and this is formed? Okay, so this is our method number two, and here I'll write method number one, and here I'll write method number two. What if it goes here and this way? Okay, so first let me complete the red steps. That is the first one. If I go by red, I will have RCHO plus R dash CHOO minus. Okay, this CH will have plus. It is a dipolar ion. This is the Zwitter ion. Okay, now this Zwitter ion will definitely have nucleophilic addition like this on the other part. And what we'll have is RCHO, this ox is here, CH R dash O O. Okay, this is what is given in NCERT directly from alkene ozone. Directly this ozonide is given. Okay, now once this ozonide is formed, you should recognize that these are the chiral centers, and there will be in all 4 isomers of this ozonide: cis dextro cis levo, trans dextro trans levo. This particular ozonide is formed. This ozonide, now with the help of any electron dense system, it could be H2O2, it could be H2O, which is the common mist, or you can use Me2S, or you can use PPH3, or you can use some 3-degree amine, etc. Any. What they will do is they will break this peroxy linkage. They will break this peroxy linkage like this, cyclic. And as you can see, if I can this. Okay, NCERT writes in a different way, but actual mechanism goes like this. So I have RCHO, I have R dash CHO, and HOH, a coordinate to a new oxygen. If you remember, it is nothing but H2O2. Okay, it is nothing but H2O2. If I do not consume this H2O2 with zinc, if I do not reduce it, okay, if we leave this H2O2, then the aldehydes formed may be oxidized, will be oxidized to acids. Okay, so H2O2 is removed, is consumed by zinc. Zinc is there to remove this H2O2, to reduce it to water and make it overall a condition which is non-oxidizing agent. Due to this reduction step, that H2O2 is reduced to water by zinc, it is called reductive ozonolysis. If zinc is absent, then H2O2 is present in the medium, and then the products are acid for aldehydes. Correct? Coming to other possibility that we left long time back here, that what if the other type of bond breakage would have taken place, that is the green one, then the Zwitter ion is of the R part and aldehyde is of the R dash part. No other difference. It is overall same only. This attacks here and it attacks here. Similar mechanism. Okay. And I think you all can now see that I'll also have the same ozonide. But yes, what if one R is H? Then definitely there will be different ozonide. What if one more H is replaced by another alkyl and so on? So there are so many possibilities, but that depends. Okay? That entirely depends. Seeing this, what I have just shown you, now you can easily understand how ozonolysis works. Okay, how ozonolysis work? It breaks the alkenes like this, correct? And we can use this particular reaction to identify the position of double bonds in alkenes. Okay, we can use this reaction. How can we use this particular reaction? Let me tell you. We can use this reaction in a different way. Say, for example, if we are told that there is something, there is an unknown alkene C6, okay, C6H12, and this particular on ozonolysis, this particular alkene on ozonolysis gives this compound. Okay, if we are told that it gives this compound, then how will we handle that? Identify the structure of this alkene. We are told identify the structure of this alkene. So what you do whenever you are given, first you count the number of carbons, C6, 1, 2, 3, 4, 5, 6. Okay, carbon number if remain intact, that means that it was a ozonolysis of a cyclic compound. You draw such thing, eliminate these oxygens, extend the double bonds. So it appears to be like this. 2 and 6 seems to be bonded. 1, 2, 3, 4, 5, 6, like this. If the same question would have said that the product is this compound, then your answer will be cyclohexene. So this reaction, ozonolysis, is used to identify the structures of the unknown compound. Okay, it is used to identify the structure of unknown compounds like this. Correct? So let us have some very important reaction. Very important example I want to give. Please note this particular very example. Polymers, use of ozonolysis to identify the monomers of a particular polymer. Okay, let me exemplify my point. I hope all of you know what is natural rubber. It is all cis polymer of isoprene. Natural rubber is all cis polymer of isoprene. Now this 2-methyl 1,3 butadiene is called isoprene. When it polymerizes, then it polymerizes like this, N number of times such units repeat themselves, and we have a polymer of this type of structure. Okay. Now the question is, what is the ozonolysis product of natural rubber? If we are asked to ozonolize natural rubber, what would be the products? So let me for that you have to write it at least 2-3 times the proper structure like this. It may go on further and further, but at least 2-3 times. Once you draw this, now we'll do polymerization. Sorry, now we'll do ozonolysis. So here it will be double bond O. Here it will be double bond O. And then we'll check, is it the same unit coming again and again or something different? Okay, so this is our Sol 1 unit. Let me write it. It is double bond O, double bond O. This is our another unit. So again I'll write. We have written just to identify that it is a repeat of similar thing or not. Okay, this is still incomplete, so I'll write it this way. But these two units are, you can see, repeat. So let me name them 1, 2, 3, 4, 5. What we have obtained by ozonolysis of this particular compound is 4-oxopentanol. Okay, so you have to know how it polymerized, and then you can do this type of ozonolysis. A question may be reversed. Ozonolysis product is given, and you may ask a monomer. That would be relatively tougher, but you need to know and you need to attempt that. Okay. So, what if in place of zinc H2O2 is there, then we'll form aldehydes to acids. That is the only difference. Otherwise, the rest will remain same. Now we are heading to our last set of today's reaction, that is hydroxylation reaction. Hydroxylation reactions. Hydroxylation reactions is basically RCH double bond CHR. Okay, the reagents usually could be, say, Bayer's reagent, which is very dilute, cold, alkaline KMnO4 aqueous, and the formation of RCHOHR. This diol formation, okay, this diol formation is known as hydroxylation reaction. We have to be very careful about the condition of word very dilute. It ranges from 1 to 2% hardly, because KMnO4 being such a strong oxidizing agent can anytime oxidize our alcohol further to either acids or ketone. So we have to be very particular, very careful about the use of dilute KMnO4. Correct? So how to use it, how to do it? Let us do a reaction with Bayer's reagent mechanism. As you all know that structure of KMnO4 is like this. K plus MnO4 minus. Okay. It is again a type of cyclic addition reaction like this. Okay. It is again a cyclic addition reaction, which we have seen in sort of ozonolysis also. Similar way it has started again. Okay. So this is how it is added to our double bond. As a result, what we have is RCHCHR, a five-membered cycle. Okay, we have got a five-membered cycle like this. Correct? Once I have this five-membered cycle, it is basically an ester of manganese. It is ester of manganese. Correct? Now this ester of manganese is hydrolyzed. So as we have discussed before, HOH, HOH, this is how it will be hydrolyzed. And again, R, CH, OH, CH, OH, R. Our manganese is H2, Mn, okay, OH, OH, double bond O. Oh, let me write it as a structure. It would be easier to understand that way. We have got Mn, OH, OH, O minus, like this. Okay. Ultimately, disproportionate, and we have MnO2 and HMnO4 along with water. This will appear as a brown precipitate. So as the reaction completes, we have an appearance of brown precipitate and a gradual decolorization of manganese KMnO4 solution. So it is used as a test of unsaturation. And see, again, it is a syn addition reaction because the cycle form was from the same side, and then it proceeded further. Okay, so overall the reaction remains syn addition reaction. Clear? We can use some other reagents also in place of KMnO4. Now, what are those other reagents? The most common is OSO4 followed by NaHSO3 aqueous or Na2SO3, or you can have other reagents to break that also. So, how does this work? Okay, how does OSO4 works? Again, same way, it is also a syn addition. CHR, double bond O, osmium. I'm taking it from one side of alkene. Similar way, we will have this type of cycle is formed. Again, when you do hydrolysis, okay, this is again syn addition. Same way, we'll have RCHOH, CHOHR plus OS, O2, OH and OH. Okay. Now, this is further oxidized back. As I said, we use NHSO3 along with H2O2. Here we use NHSO3 plus H2O2. It oxidizes back osmium to OSO4. So we use it back to OSO4. The osmic acid formed is further oxidized by the use of H2O2 to OSO4. Now, this is a very good yield reaction. Okay? And very specifically syn. All goes well for this reaction, but osmium is poisonous. So, as the compound itself acting as a poison, therefore, we would avoid use of osmium. Therefore, OSO4 is not allowed in laboratories, not allowed in labs. Otherwise, this is a better reaction because it won't oxidize further our diols to alcohol to acids. It will stop the reaction at that stage. Whereas in KMNO4, there is a great fear. What if KMNO4 is taken slightly strong? It will break completely our alkene. If I take just alkaline KMNO4 and forget to keep the dilution, or if I forget to keep the cold condition, this will just go to 2 moles of acid. That is the strength and the drawback with KMNO4. No such problem with OSO4. Okay, if I just forget, and then here I will have RCOH and formic acid. If further heated, or if the conditions are acidic KMNO4, this formic acid may easily be oxidized to CO2 very easily. So we have to be very particular about the concentration conditions and the temperature conditions when we use KMNO4. But with OSO4, no such problem. So, ideally, as per chemistry, we should use OSO4. But as it is poisonous, it is not allowed in the laboratories. Is that okay? So, this is our all the 4 reactions that we targeted today are complete. Okay, next is their polymerization that think all of you know. That is not such a tough reaction, but I'd like to conclude the uh, the test for alkene conformation in lab. Unsaturation. First is the bromine water decolorization test. Test, and second is the Bayer's reagent decolorization test. These two are used as a confirmatory test for presence of alkenes in a given condition. Okay, so that brings us to the end of our today's lecture. Tomorrow we'll discuss conjugated alkenes, that is 1,4 addition of andines, along with alkynes. Okay, alkynes are more or less extension to alkenes. So we have to go through similar reactions, but as there will be 2 double bonds, slight changes definitely are expected. Okay, so tomorrow we'll meet again at 10 a.m. sharp in the morning for alkynes. Till then,